This meeting is being recorded.
Okay, so welcome everybody to today's IAMP seminar. It's a great pleasure to introduce Daisuke Shiraishi from Kyoto University. And the title of today's seminar is Recent Progress on Loop Erase Random Walk in 3 Dimensions. And let me say that as usual, the seminar will be recorded and made available on YouTube. And I leave the floor to Daisuke. Thank you very much.
Okay, thank you for the introduction. First of all, I would like to thank the organizers, especially Tasaki-san, for giving me the opportunity to talk here. Today, I'm going to talk about loopless random walk. While focusing on the 3-dimensional case. This talk is mainly based on the joint work with Xinyi Li from Peking University. Okay, so let me start. Let me begin with the introduction of the loopless random walk in this slide. Actually, I will focus on the loopless walk in the ZD lattice case later in the talk, but in this slide, let us consider the general setup. Okay, so suppose we have a graph G, which is finite and connected, and we take a point V and a subset A. Okay. And okay, so let S be the simple random walk on the graph G, starting from point V. And we consider the simple random walk until the first time that it hits the subset A. The first time is denoted by large T. Okay. So here is the loop erasure denoted by LE. We erase all loops from the simple random walk path chronologically. I mean, okay, so let me draw the picture. Yes, here. Okay, so whenever the simple random walk create a loop, something like this, then you erase the loop chronologically. So we have a simple path from V to A. Okay. So this is a loop erasure. And this loop erasure of the simple random walk path is called the loopless random walk from point V to subset A. Okay, so it was originally introduced by Greg Lawler. So he's here, and about 40 years ago. Okay, so by definition of the loop erasing procedure, it is easy to check that the loopless random walk is a simple random simple path contained in the original simple random walk path, and it starts from point V, and its endpoint coincides with the endpoint of the original simple random walk, say S of T. Okay. Okay, so this is a picture of, So this is a picture of planar loopless random walk, starting from the origin to some circle. Okay, good. So in this slide, I will explain some alternative definition of the loopless random walk that is Laplacian random walk. Okay. So the setup is the same. So we have a graph, the point V, and subset A. Okay. So let gamma be the loopless random walk from the point V to the subset A. Okay. Okay, so I'm interested. I want to know how the loopless random walk evolves by looking at its transition probability given the path. So we take the path lambda, it is a simple path, as a candidate for the past part of the loopless random walk up to time m. Okay. So, as I said, I'm interested in the transition probability of the loopless random walk given the past. So this one. And in order to compute this transition probability, basically we need to prepare the following discrete harmonic function. So let me draw the picture. We have path lambda here and subset A like this, and they do not intersect each other. And discrete, so let us consider function f that is a discrete harmonic on the complement of the path lambda and subset A, and whose boundary condition is given by the first item. That is, f, the function f vanishes on the path lambda, while it is equal to 1 on the subset A. Okay, so like this. So these two conditions determine the function f uniquely. So using this harmonic function f, this transition probability of the loopless walk is given by the average of the harmonic function among all nearest neighbor point of the tip here, tip of the past part, say lambda over. Okay. So in this sense, at each step, you need to compute the discrete harmonic function in order to know how to move in the next step. Okay. So this is the evolution. And I am writing this formula 1 again here because it is important. And looking at this formula, you see the loopless random walk is not a Markov process. Okay. But so here, let us think of the loopless random walk as evolution of sets. I mean, okay, again, let me draw the picture. I mean, given the past part of the loopless walk, from this point of view, your current position, your present position is not a chip, but the whole set. This one, whole set of the past. Okay. Then, given the whole set of the past, using the formula 1, basically, you can compute the discrete harmonic function f, and you know how the set evolves in the next step by using this formula 1. Okay. So in this sense, the loopless random walk satisfies some Markov property that is called the domain Markov property. Okay. Okay. So actually, the proof of this formula 1 is very, very easy. But analyzing the loopless random walk is normally a difficult problem. For this, for example, you can imagine the diffusion limited aggregation, say DLA. For the LA, it is also described by dynamically changing harmonic measures. But yes, for the array, almost nothing is known rigorously. But the message of this talk is that the loopless random walk is one of the few critical models arising from statistical physics where we can analyze it in a mathematically rigorous manner. So I will explain this later in the talk. Okay, so before going to the next topic, let me remark the following interesting open problem. Okay, so as I explained, the discrete loopless random walk satisfies the formula 1. But as usual, we are also interested in the scaling limit of the loopless walk. So the question is, what about the formula 1 in the continuum setting? Yes, of course, in the continuum setting, we expect that the evolution of the scaling limit is also described by dynamically changing harmonic functions. I mean, the continuum harmonic functions, similarly to the discrete case. But as far as I know, for the general setting, formulating such a Laplacian motion in the continuum setting has not been established yet, because the formula 1 is not easy to make sense for the continuum setting. Okay, so this is some remark. Okay, so I will move to the next topic, that is uniform spanning tree. So again, suppose that we have a graph G, which is finite and connected, okay? And as usual, a connected subgraph with no cycles is called a tree. Okay? And also we say a subgraph is spanning if it contains all vertices of the graph. Okay? So here is the uniform spanning tree. Because the graph is finite, so of course the number of spanning trees is also finite. So we can choose a random spanning tree uniformly at random. So it is called a uniform spanning tree. Okay, so again, this is a picture of the uniform spanning tree in planar uniform spanning tree in a large box. Okay, so what is the relation between the uniform spanning tree and the loopless random walk? Actually, there is a very, very beautiful algorithm to generate uniform spanning tree using many loopless random walks. It is due to David Wilson. So what is his algorithm? So in the algorithm, you first choose the arbitrary ordering of the set of vertices, say Vi. Okay, and after that, you consider the loopless random walk from V1. Yes, from V1 to V2. It is denoted by U1. Okay. And in the next step, you take the loopless walk from the third point to U1. And these two loopless, the union of these two loopless random walk is denoted by U2. Okay. And you continue this attachment of loopless random walk from a new point to the previous subtree. Okay. Until all vertices are contained in your tree. Okay. So the surprising result proved by David Wilson is that your final output is always distributionally equal to the uniform spanning tree. Okay. So in this sense, the uniform spanning tree consists of a number of loopless random walks. And also, let me mention that the following immediate corollary of Wilson's algorithm. Yes, using his algorithm, we know that the loopless random walk from V to W is distributionally equal to the loopless random walk from W to V, because both sides coincide with the branch of the uniform spanning tree between V and W. Okay. So in this sense, loopless random walk satisfies the reversibility. Yes.
Question?
Yes.
So is this a way that you easily prove this reversibility? It's a surprising property, but are there direct proof without using
Yes.
spanning tree?
As far as I know, yes. Greg Lawler proved in his textbook. I have this one. Maybe, yes.
Yeah, he confirms it's correct. So the God is here. Thank you.
Okay, yes. There is another proof, elementary proof by induction, but so anyway, so this is the relation between uniform spanning tree and loopless random walk. I will talk about some applications to the uniform spanning tree, given some information about the loopless random walk later in the talk, if time permits. Okay, so from now on, I will focus on the loopless random walk in 3D lattice, and mainly focus on in the three-dimensional case. So let us be the simple random walk in 3D lattice, starting from the origin. So I write Tn for the first time that it exits from the ball of larger set. Okay. Okay, so let gamma n with loopless random walk from the origin to the boundary of larger set. I'm interested in the following two objects. The first quantity is the length, the number of lattice steps of the loopless random walk. It is denoted by Mn. The second quantity, a second object, is the scaling limit of the loopless walk as the mesh size goes to 0. So the question is, does the scaling limit exist? And if so, what are the properties of the scaling limit? And can we characterize or identify the scaling limit? And so on. Okay. And concerning the scaling limit, let me mention that there is no simple loop erasing procedure directly from Brownian motion, because the Brownian motion has a loop at every scale. So the first loop of the Brownian motion does not make sense. Okay? So unfortunately, we cannot say that the scaling limit is given by such a loopless Brownian motion. So this is a remark on the scaling limit. Okay, so in this slide, I will explain some known results about the loopless random walk in ZD lattice, except the three-dimensional case, very, very briefly. Okay, so because if the dimension D is bigger than or equal to 2, then the simple random walk in ZD lattice is always the two-dimensional set. So from this fact, it turns out that the critical dimension of the loopless random walk is equal to 4, which is 2 plus 2. Okay, in fact, I mean, if the dimension D is bigger than or equal to 4, then a loop of the simple random walk is only local. Namely, it doesn't have a macroscopic loop. Yes, in fact, Greg Lawler proves that if the dimension D is bigger than or equal to 5, then the loopless walk is still the two-dimensional set. Okay. And the scaling limit is the Brownian motion, similarly to the simple random walk case. And in the critical dimension, I mean, for the four-dimensional case, still he proved that the loopless walk is again the two-dimensional set, but we need a log correction to describe the asymptotic behavior of the expected length. So the exponent is 1/3. Okay. But the scaling limit is again the Brownian motion. Yes, as you imagine, in the low dimensions, the situation is completely different, and basically it is more complicated. But for the two-dimensional case, it is nice in the sense that we can use the conformally field theory to analyze the loopless random walk. In fact, Richard Kenyon proves that in 2 dimensions, the loopless walk has dimension 5/4. And for the scaling limit, it is proved that the scaling limit of the loopless random walk, planar loopless random walk, is conformally invariant. It is given by the Schramm-Levner evolution, SLE, with parameter 2. Yes, there is a big and beautiful progress for the two-dimensional case, but I'm not going to the details anymore because I want to focus on the three-dimensional case. Okay, so the question I want to consider in the rest of the talk is the following. So what about the three-dimensional case? So the quick answer for this is that we can do something, but it remains poorly understood. So in the rest of the talk, I will explain something about the three-dimensional case. Okay. So recall the setup. The gamma n stands for the loopless walk from the origin to the ball of largest n. And we write mn for the length of the loopless walk. Okay, so the first result about the three-dimensional case was obtained by Greg Lawler. Okay. He proved that the expected length satisfies this inequality. So it says that the dimension is strictly bigger than 1, and it is smaller than 5/3. Okay. So this means the loopless random walk is not like a straight line, because dimension is bigger than 1, strictly bigger than 1. And on the other hand, it is completely different from the original simple random walk, because 5/3 is strictly smaller than 2. Okay. So what about the scaling limit? So for the scaling limit, Gardy-Kozma proves the following remarkable result. So, okay, here let us think of the rescaled, this one, rescaled loopless random walk for the dyadic scale as a set, as a random subset in the Euclid space. Then as the mesh size goes to 0, he proves that this rescaled loopless random walk converges weakly with respect to the Hausdorff distance topology. Okay. So in this sense, we know the existence of the scaling limit. And moreover, he proves that the scaling limit is invariant under rotation and direction. Okay. Okay, so given these two results, I wanted to understand the sharp asymptotic behavior, of the length, the expected length, I mean, this quantity. Of course, it seems quite hard to determine the exact exponent for this expectation. But even the existence of such an exponent helps us to push our work of the loopless random walk forward. So with this in mind, the next theorem guarantees such an existence of the exponent. So it states that, yes, there exists some exponent, some constant beta, such that the expected length is of order n to the beta. Okay. So this constant beta is called the growth exponent. Unfortunately, the exact value of this exponent is not known, but numerical simulation suggests that beta is around 1.624, Okay, so in the next 2 slides, I will try to explain how to prove this theorem. Yes, actually, this theorem is the only place the proof is explained. Because fortunately, the proof is not complicated. And I think it helps to get a feeling of the loopless random walk. Okay, so what is the proof? Okay, so first of all, in order to prove the existence of such an exponent, a standard technique is a subadditive argument. But I think it is not easy to use a subadditive argument for the expected length directly. So I choose a different approach to get a theorem. Okay, so I rewrite the expectation, the expected length by the sum of hitting probability. Yes, the hitting probability of the loopless walk to the point x. Okay. So by definition of the loop erasing procedure, actually this hitting probability is exactly equal to the loopless random walk from the origin to the point x, does not intersect with simple random walk from point x to the boundary. Okay. This follows from the definition. More precisely, I decompose the path at time sigma x. It is the last time that the simple random walk hits x. Okay, now record the reversibility of the loopless random walk. So now we consider time reversal of the loopless random walk. So this one. Okay. Then you can imagine that the right hand, the probability in the right hand side, so this one, is related to the following escape probability, say ES of scale n. So where the escape probability is defined by the non-intersection probability of the loopless random walk and independent simple random walk, where they start from the origin up to the larger n. Okay. In fact, this hitting, you can prove that this hitting probability is comparable to an inverse multiplying this escape probability if the point x is located in the typical place in the ball of larger n. Okay. Yes, of course, this n inverse corresponds to the probability that the original simple random walk hit the point x. And this escape probability, of course, corresponds to the probability that the point x is not erased. Is not erased in the loop erasing procedure. Okay. Okay, so given this equation, of course, the problem boils down to the asymptotic behavior of escape probability. I mean, we need to prove that there exists some constant alpha such that the escape probability is of order n to the minus alpha. Okay. Okay, so for that purpose, let us consider the ratio. The ratio of two escape probabilities for the dyadic scale. Okay. So let me draw the picture for this ratio. So this ratio consists of the escape probability of loopless walk and simple random walk up to 2 to the n plus 1 divided by the same type of non-intersection probability up to 2 to the n. Okay. Okay, so this is Polish. Okay. Okay, so here is the heuristic argument, right? Very, very roughly speaking, if you take the ratio, then the no-intersection probabilities coming from the inside of the ball of radius 2 to the n should be canceled, okay, in the ratio. Yes, in fact, you can prove that this ratio is well approximated by some constant, universal constant C0, multiplying the alternative non-intersection probability. That is the non-intersection probability of loopless walk and simple random walk. But they start from the pole, 2 poles of radius 2 to the n, up to the next level. Okay. So actually proving this approximation is a main contribution of the theorem. Okay. And once we get this approximation, the remaining story is relatively simple. Actually, taking the scale n sufficiently large, you know, the loopless random walk, this solid curve, simple curve, is approximated by Kozma's scaling limit, starting from the pole of radius 2 to the n. And of course, the simple random walk, you can replace the simple random walk by the Brownian motion, this dotted curve, okay? But, you know, for the non-intersection probability for this continuum curves, I mean, dotted curves, we already know that they are direction invariant. Okay? So the non-intersection probability for these continuum stuffs is exactly equal to the probability that the scaling limit and Brownian motion do not intersect, but where the starting point of them are the poles of the unit ball up to the next level. Okay. So the quantity in the right-hand side is really nice because it does not depend on n. Okay. So we can denote it by the constant p. So, okay, so the, yes, the main part is over because taking the product of the ratio of this, we see that the escape probability, at least for the dyadic scale, is given by p to the n. And here's alpha. So alpha is defined by rewriting the probability p in this fashion. Then using this alpha, we know the escape probability satisfies the desired asymptotic behavior for the dyadic scale. And for the general scale, basically you can approximate it by the nearest dyadic scale. So we have a desired estimate for the escape probability. And the proof is completed by defining the growth exponent by 2 minus alpha. So this is
so
yes.
Daisuke, do you know anything about this constant C0? So you said it's a universal constant.
Yes, I think that's just a constant, and So we don't have much information about this constant. Of course, it relates to the value of the exponent alpha, but
Yes.
I think yes.
Yeah, thank you. This is amazing.
Okay, so this is the story of the theorem, first theorem. Yes, as I said, the value of the exponent is not known, but the existence of the exponent plays an important role to strengthen Cosmos result in the following way. Okay, so again, recall the setup. Gamma n is a loopless walk up to the ball of largest n, and beta stands for the growth exponent. Okay, so the second theorem strengthen the Cosmos result. I mean, in this theorem, we consider loopless random walk as a process, not as a set. Okay, so here we consider the rescaled, I mean, time and space rescaled loopless random walk. Okay. Then the statement is that this converges weakly with respect to the usual uniform convergence topology. Okay. And unfortunately, the proof of this theorem is quite long and complicated. So I'm not going to explain how to prove this theorem. But instead of that, let me introduce various properties of the scaling limit. So let eta be the scaling limit of the loopless walk as a process. Okay. Then the next theorem shows that with probability 1, so eta is a simple curve. That's not trivial. And the Hausdorff dimension of the trace is equal to the growth exponent. And similarly to the Brownian motion, eta is not is h-held if the exponent h is strictly smaller than beta inverse, but it's not beta inverse held. Okay. Okay. Yes. We obtained these statements by pushing the knowledge of discrete loopless random walk to the scaling limit through the convergence derived in the second theorem. But, you know, for example, for the Brownian motion or for the SLE curve, you can prove a similar statement only by dealing with the continuum stuff directly, not by passing through the discrete object. That is my desired situation. But so far, unfortunately, for the three-dimensional case, for the three-dimensional loopless random walk, the only way is to make a detour passing through the discrete loopless random walk. So it is a future problem to find a nice way to remove such a detour passing through the discrete object. Anyway, okay. So in this slide, let me introduce some application to the uniform spanning tree very, very quickly because, yes, because of the time. Okay, so yes, for the uniform spanning tree, again, I'm interested in the scaling limit. But we need to be careful with the topology, the choice of the topology. So look at this picture. Okay. So this picture stands for the uniform spanning tree on the box, three-dimensional box with a fine lattice spacing. If you think of this uniform spanning tree as a set, then as the mesh size goes to 0, of course, the scaling limit is the box itself. Okay? So nothing interesting happens. So this means the choice of the topology is not good. So with this in mind, let us consider uniform spanning tree as a metric space endowed with the graph distance. Thanks to the Wilson's algorithm, the graph distance for the uniform spanning tree is given by the length, the number of steps of the loopless random walk. And as I explained in the previous slide, we have a nice control of the length for the loopless random walk. So yes, using the information about the three-dimensional loopless random walk, we know the existence of the scaling limit for the uniform spanning tree in 3 dimensions as a metric space, where the topology is the Gromov-Hausdorff-Bloch topology. And various fractal nature of the uniform spanning tree were also studied, but I think because I don't have enough time, let me skip the detail. Okay, so as a final topic, I choose the inverse procedure of the loop erasing. That is the loop addition. So the question is as follows. So what are loops erased in the loop erasing procedure? Okay, so to answer this question, let me first consider the following loop measure for the discrete stuff. Okay, so let me draw a picture again. So suppose that we have a loop, lambda, in ZB lattice, whose starting point coincides with the end point. Okay, good. With time time duration 2n, and the random walk loop measure, say mu RWL, assign the simple random walk measure multiplying 2n inverse. So let me briefly explain the meaning of this 2n inverse here. Look. Okay, so a loop with fixed starting point is called a rooted loop. Okay. But on the other hand, unrooted loop is obtained by forgetting the starting point. For this, more precisely, so let us consider the equivalence between two loops by shift of the starting point. So these two loops are equivalent. So unrooted loop is defined by the equivalent class of this relation. And basically, we want to assign the simple random walk measure for each unrooted loop. So that's why we put 2n inverse here. Okay. So how to compute this loop random walk loop measure? Basically, you first consider all possible time duration and all possible starting point of the loops. And once they are fixed, of course, the loop measure is described by the simple random walk probability. Okay. And I rewrite this probability by the random walk bridge measure multiplying the return probability. Okay. So this is a discrete loop measure. So what about the continuum setting? In the continuum setting, we can define the similar loop measure, which is called the Brownian loop measure, UBL, by replacing 2n with time t and replacing the random walk loop bridge measure by the Brownian bridge measure, and finally replacing the return probability by the hit kernel. Okay. So this is a Brownian bridge measure. Okay, so let us consider the person point process with whose intensity measure is the Brownian bridge measure, Brownian loop measure. So this person point process is called the Brownian loop soup. It was originally introduced by Greg and Wendelin Werner. Okay. So this picture stands for the realization of the Brownian loop soup. It is a collection of random loops like this in the Euclidean space. Okay. So by using this Brownian loop soup, we have the following decomposition of the Brownian motion. So this is the final theorem. So it roughly states that in 2 and 3 dimensions, the scaling limit of the loopless walk plus the Brownian loop soup is the Brownian motion. So the precise meaning of this is as follows. Okay, so this is a unit ball, and here is the origin. Suppose that you have a scaling limit of the loopless walk. It is a simple curve connecting the origin and the unit ball. Okay, and also you have a Brownian loop soup, the independent which is independent of the scaling limit. So the realization is like this. Okay, but we only use the loop contained in the unit ball, and also we only use the loop which intersect with the scaling limit. So the picture is something like this. Okay, so we don't use these loops. Okay, then the statement is that if we consider union of these loops intersecting the loopless random scaling limit plus the scaling limit is distributionally equal to the Brownian motion. Okay. Yes, actually, this is a result for the continuum setting, but for the discrete setting, it was already proved by Greg and Limit. This is a textbook on the random walk. Yes, I think yes, I have a book in the back. But anyway, for the discrete setting, it was already proved. But yes. And another remark is that you can find some similarity in the excursion theory introduced by Kiyoshi Ito for the one-dimensional Brownian motion. So his excursion theory guarantees that a collection of loops created by the one-dimensional Brownian motion is also described by a single person point process. Okay. Of course, for the one-dimensional case, we have much more information about the decomposition. And a number of applications of excursion theory have been established. But for the multidimensional case, unfortunately, so far we have only this decomposition. I mean, a nice application is not found yet. By the way, Ito sensei is my great grandfather in the academic sense. Yes, anyway. But still, I'm interested in this decomposition because of the following conjecture. The conjecture states that this theorem characterizes the scaling limit of the loopless walk in 3 dimensions. So the precise meaning of this is as follows. Okay, so imagine that you have a random simple curve from 0 to the boundary. Okay. And suppose that you have a Brownian motion. If you add the Brownian loop soup, similarly to the theorem 5, then the conjecture says that your original random simple path must be the scaling limit of the loopless walk. So yes, in this sense, we want to characterize the scaling limit as a subtraction. The subtraction of Brownian motion and the Brownian loop soup. But you see, this subtraction is not standard. So this conjecture still remains open, I think even in 2 dimensions. Okay, so let me summarize this talk with a short sentence. So my message is a 3-dimensional loopless walk is in some sense analyzable, but as you see, it is still wrapped in mystery. Okay, so it's time to stop. So thank you for your attention.
Thank you very much for this very clear and beautiful talk. Is there any question or comment from the audience?
Perhaps one question. Mm-hmm. Can you compare the the loop with erasures with self-avoiding walk? For instance, the diffusion would be more or less the same, or?
I think self-avoiding walk is, first of all, self-avoiding walk is much harder than the loopless.
Sure, harder to study, yes. Mm-hmm.
And people basically expect that they are different. For example, in 4 dimensions, the exponent, the critical exponent is 1/3. Proved by Greg. But if my memory is correct, for the self-avoiding work, it should be 1/4.
Correct.
Yes.
Mhm.
And in low dimensions, for the self-avoiding work, basically, rigorously speaking, we don't have much information. But in 2 dimensions, yes, again, Greg, Odette, and Wendelin propose that the scaling limit is given by SLE with parameter 8/3, if my memory is correct. Yes. So that should be different from the loopless work. And in 3 dimensions, I don't know.
If I could add a bit in 3 dimensions, the Flory prediction in 3 dimensions was basically that a certain quantity was 0.6, which was basically an exponent. I mean,
So Flory
I'm trying to remember the algebra, how you get to.
Mhm.
The 0.6 I'm talking about, I think, is 1 over this beta.
Mhm.
I think
So
it's one
there was
over
a
beta.
Flory exponent, and basically I proved that the loop race walk was thinner than what the Flory exponent would predict. And the current predictions for self-avoiding walk is that self-avoiding walk is actually just a little bit fatter than the Flory predictions, which are expected to be wrong. So this 0.6 is about 0.61 for loop race and about 0.588 for self-avoiding walk. So they're expected to be different universality classes.
Thank you.
Very interesting. Yeah, can I ask a question? So some part of your work is based on something you called Cosmos scaling limit.
Right.
But you also had a better scaling limit. So what is this Cosmos scaling limit? So there's no non-trivial scaling exponent in this scaling, right? So but do you still have a
because he regarded the loopless walk as just a set.
okay.
So basically, you need space scaling factor only.
So this is not the scaling that I'm a physicist, so this is not the correct scaling that we call, but yours is the correct scaling limit, right?
Yes.
But that's amazing. That's very interesting that still this Cosmos scaling limit was useful in your proof of the existence of exponent. Why was it useful there?
Yes, the story is the following. Basically, by the Cosmos scaling limit, Cosmos result, we know that the scaling, we have some set as a scaling limit, but extra work, additional work is needed to get the second theorem because we need to parameterize. We need to parameterize this path appropriately because because in this theorem, we consider loopless random walk as a process. So the time parameterization is important. So, yes.
Yeah, okay, thank you.
Other questions?
What was the original motivation for introducing this this process? So, as I understand, this these uniform trees is one of motivations. What
Right.
are there any other motivations?
Are you asking Daisuke or the inventor?
Maybe I should answer that. The original motivation was to try to understand processes with self-avoidance. So the idea was to understand, just the idea of loop erasure actually came from my advisor, Ed Nelson, as a suggestion for a thesis project, to see what you get if you erase loops. And as I tell people now, the bad news was it was not the same as self-avoiding walk. The good news was it was a very interesting process in itself.
Thank you.
Are there
The
other
uniform spanning tree relation was found by others later. It was not found originally by me.
Are there other comments? Please, David, yes.
Could I ask a question?
Yes.
Is there a stochastic differential equation for loop erase walk? I mean, with some, there is for self-avoiding walk, and I'm wondering if there is one for loop erase walk.
So in two
Can I ask
dimensions.
what you mean for self-avoiding walk?
Sorry, what did I said, I think there is one for self-avoiding walk. No, that's actually true self-avoiding walk for which there is one. I was wondering if there is one for loop erase walk.
In two dimensions, of course, SLE gives some differential equations, but in three-dimensional case, for the three-dimensional case, it's not found yet.
Mhm.
If you don't mind, I would say what exists in two dimensions is a differential equation or stochastic differential equation for a conformal map on the complement.
Yes.
Even in two dimensions, there's not a direct stochastic differential equation for the path.
Yes.
In the sense that I think, that's why I was asking the question about what you meant for self-avoiding walk. The idea is, well, what does this mean?
Mhm.
I would say no.
Okay, yes, because yes, there are really three processes that create sets that don't self-intersect. Loop erase walk, what people call self-avoiding walk, which actually isn't a process, but might be, I suppose, in a limit. You thought about that, Greg. And then there's also true self-avoiding walk. And as far as I know, they're all different.
Yes, let me add, there's an infinite family of paths that produce self-avoiding things. In two dimensions, the SLE kappa is a continuous parameter. But even in there, you can also think in more than two dimensions, you could think of Laplacian random walk, which Daisuke mentioned here, you can give a parameter for the Laplacian random walk telling you the exponent of the solution of the Laplace's equation you're using. And say in 2 dimensions, the self-avoiding walk in 2 dimensions is conjectured to be the same roughly as a Laplacian walk with exponent 5/8. Now, whether the self-avoiding walk in 3 dimensions is a Laplacian random walk with a particular exponent is unclear. In fact, even defining the Laplacian random walk, I call Laplacian motion for the continuum limit, which we don't know that it's, yeah. Okay, there. I'm sorry, the important open problem is there.
Yes.
Yeah, for anybody who doesn't know what true self-avoiding walk is, roughly speaking, it's a stochastic process where you decide where you're going to take your next step on the basis of choosing the randomly from the nearest neighbor points next to the place you're currently occupying, with the rule that conditioned on it not being in the walk that you already developed.
Yeah, this is sort of a different class of process. In fact, in my first book a long time ago, I tried to use the word myopic self-avoiding walk for this process. Myopic meaning nearsighted. All these Laplacian motions, you take your next step based on looking at your entire past. While this sort of true self-avoiding walk, which is not true at all, is based on the property that you only look at your nearest neighbors and how many times you visited them for your motion.
Other comments or questions? Doesn't seem to be the case. So let's thank again Daisuke for the very nice presentation.
Thank you.
Thank you.